Okay, so we're looking at exponential functions today and the key characteristics. What's important is that you can move between a graph and a general expression of the exponential function. One of the key things we're going to pick up on is that a general expression of a exponential function is proportional. One of the difficult parts today is this goal. This one, I'm not sure how this one's coming up in testing. So we're going to have a good look at what happens when we transform exponential functions, because it's the additive transformation that creates the most problem. That's this one here. And there is a specific goal that we have to cover on that one. So in exponential functions, here's a bit of a recall of all the information that we know. So we should have seen exponential functions last year. We often use this for interest and currency when we're looking at things going up and going down. We use them for population growth and radioactive decay. Hopefully you've seen half-life before and the spread of diseases. So these are topics that are common to IM3 that you should have studied previously. When looking at exponential functions. So
it's the accessibility. It doesn't make sense.
So one of the key parts is that an exponential, we'll talk about exponential functions and we'll talk about exponential functions in general form. Look carefully for the wording changing in questions sometimes. So an exponential function in general form. An exponential function in general form, that's this part. It doesn't have any horizontal or vertical translations in it. So an exponential function in general form looks like this. There's no horizontal translations, no vertical translations in it. Now, when we do that, we have to have the constant a not equal to 0. Why does a not have to be 0? Why does a have to not be 0? You wouldn't have a function. You wouldn't have a function. But more importantly, why can b not equal 1? Yeah. If b is equal to 1, the function's not going to be going up or down. It's just going to flatline. It's not really much of it's not an exponential function. It's only going to be y equals a. It's only going to be y equals a. Some bits and pieces we do know about this is that a represents the initial amount. This is where it's crossing the y-axis. A represents the initial amount. This is when we're referring to general form. B represents the base, or if we're talking about a geometric series, it's the common ratio. And then we get two types of graph. We get exponential growth, and it's essential that so here in the exponential growth, it's essential that we identify that b is greater than 1. A has to be positive, otherwise it's going to be going down below it's going to cause a reflection. We're not usually looking at that one when modeling real world situations. It's not so useful. And then for exponential decay, we get this. So I think this is some of the most important key facts we need to memorize and remember. Is for growth, we have that, and for decay, we get this. So make sure we memorize that fact. So what can we say about an exponential function? Well, an exponential function is monotone. Monotone. So it's a monotonic function, which means it's only moving in one direction. It's either only going up or only going down. It doesn't go up and then down. It only has one direction. So it's either always increasing or always decreasing, which means they're not going to switch from one direction to the other, which means they can't have a local extreme point. They have a maximum and minimum because that's the endpoints. If it's a restricted domain or restricted interval, the max and minimum will be on the two endpoints. If it increases and decreases, if x increases and decreases without bound, then it's going to go towards 0 at one end and go towards infinity at the other one. And these will be the maximum and minimum.
Does an exponential function always have an asymptote?
Yes, it always has a horizontal asymptote. And typically that, if it's in general form, that's always y equals 0. So can anyone explain what a relative extrema is? Let me have hands. Who wants to explain to Danny? Perfect. All right. So the other one is that if it's always increasing, it's always concave up. So if we notice this one here is always increasing, it's always concave up. Whereas if it's always decreasing, it's always concave down. Sorry, no, what am I talking about? No, it's not. This one's also concave up. How do we get it to be concave down? It says here it can be concave down. How do we make that happen? Abdullah. Yeah, if you have a reflection in it, it's going to be concave down. So if A is less than 0, negative, you're going to get a reflection, and it's going to be going down, and you'll get concave down. And that also means that we're never going to switch concavity. So if it's concave up or concave down, we're never switching concavity, so we can't create a point of inflection. So it's going to have no points of inflection. The end behavior. So exponential functions in general form. Notice that we're using the wording in general form. As the input value. So let me pause on this one. This paragraph is one of those that we memorize. It's the answer to one of the test questions in the test. This paragraph and the wording of this one is a memorization one. Okay? So, exponential functions in general form, as the input values increase without bound, the output values will increase without bound, or so on, or vice versa. So, here, this phrasing, we could say, oh, you'll be asked to describe the end behavior of a exponential function. You'll look at it. Let's take that one there. And as x increases without bound, the output values will increase without bound. So when you're asked to give the end behavior, you should always give it in this wording statement and then as a limit statement. Whenever you're asked to give the limit statement, give the word one as well. Always give both of these. So the end behavior of a limit statement says that as x approaches infinity, the limit value will approach infinity. One thing I want to mention about the performance recently in the exam is you had a bound question and you were asked to say what will happen as x approaches without bound. You had to answer, and it wanted the limit statement. You had to answer in words and the limit statement, and some of you got no points. Some of you got no points because it said what happens as x increases without bound, and you gave both. You said as x approaches infinity, y will go to infinity. As x approaches negative infinity, y will go to negative infinity. If you give both and it asks for one, you get no points because you're showing you don't understand what the question means. That seems harsh. That seems harsh, especially when, you get all or nothing on these type of questions. There isn't really much scope for half marks. So you have to only answer what the question asks. Okay. All right, let's have a go at some of these. So write limit statements for the end behavior for the following exponential functions. I'm going to do the first one, and then I'm going to ask you to do the other ones. So I'm going to write it just in limit statements, but if I was in an exam on a free response question, write both. But on this one, I'm just going to practice writing the limit statement. So when it came to writing limit statements, this mathematical syntax is precise. And a lot of you, I gave the point when you misused the limit statement notation, if you didn't format it correctly this time. But next time, I will not. So the left limit. So the left limit, we're looking at the function over here. We're looking at what's happening there. That is the limit. That is the limit as x approaches negative infinity. Now, it's really important that this statement of x approaching negative infinity is under the lim, the lim. This is the Greek word lines for limits. And the limit of, what's the function called? Are we told any name? No, we're not given a name. F of x is equal to 0. And the limit as x approaches infinity of f of x is equal to infinity. I'm going to write it like that from this point onwards because I'm looking at how the mark schemes are and I'm going to match with the vocabulary that they're using. If in an IB exam, if the right-hand limit, sorry, I've missed a bit. This is the left-hand limit. No? Sorry, I'm missing a bit. As x approach, no, I'm right. In an IB exam, we would have to say that the limit value does not exist when we go to infinity because you can't get to infinity. Nothing can equal infinity. But looking through the way that they're marking in the AP exam, they're going to have it equal to infinity. So from this point onwards, I'm just going to do that. All right. Have a go at B and C for yourselves. I'll give you 2 minutes for that. Okay. So looking at our limit statements on this one. So here, the left-hand limit would be the limit as x approaches negative infinity. And I'll call this one g of x is equal to negative infinity. And the limit as x goes towards infinity of g of x is equal to 0. Let me just check that, yeah. Okay, so for this one, is the graph going to be increasing or decreasing? Can we do a little sketch of it? Is this a growth or decay? Decay. Why is it decay? Sorry, let me take somebody fresh. Shana. Because b is less than 1. Because b is less than 1. It's between 0 and 1. So we are going to be doing this one, aren't we? Or are we going to be doing this one? Why is it the first one, Danny? Because A is not negative, there's no reflection, it's going to look like this. So, what is our limit? So, the left one. So, the limit as x approaches negative infinity, does this one have a name? It's g of x. And g of x is equal to infinity. And the limit as x approaches positive infinity of g of x is equal to 0. Okay, next. For each of the following, determine if the exponential function is increasing, decreasing, concave up, concave down. So this isn't going to take much time. We'll do this first one together. Is this graph concave up or concave down? Concave up. Is it increasing or decreasing? Decreasing. What is the possible values of A and B? What is the possible values for A? What is the possible values for B? Look, I was being lazy. Yeah. I like that. All right. Should we do this one? I might as well do these all together. Discuss with the person next to you. Are we concave up, concave down, increasing, decreasing? What's A and B? Bassam, you want to sit here and you guys discuss? You guys want to sit on the, so you have somebody to discuss with? All right. Concave up or concave down? Sorry, let me have quiet. Can we have quiet, please? Let's have something from Hassan and Zach. We're concave down. We're concave down. Increasing or decreasing? Decreasing. What's the value of A? B? Which one's it going to be? Yeah. This one's going to be greater than 1. Is that correct? No. You're forgetting the reflection. We're reflected. Oh, sorry. I'm wrong. All right. No, we are right. That's A. Okay. Forget that, silly teacher. Okay. Discuss with the person next to you. Do a quick sketch of this one. All right. Let's have a look. It's going to look like this, isn't it? It's going to look like this. Where does it cross the y-axis? It's going to cross here at 0,3. Are we concave up or down? Are we increasing or decreasing? Increasing. Okay. So we're going to go from ridiculously easy to hold on to your pants at this point.